Today, you and I have a daunting task, and that task is to try to understand what electricity actually is. And to do that, we're going to need to look at an electric circuit and figure out how electricity flows and how energy is transferred from something that generates electricity into some type of an electrical load. And we're also going to take a close look at the units of power and energy and see if we can't, wrap our mind around what they actually are. It's amazing in our modern world where we count on electricity for lighting and heating and, all the modern conveniences that we have, how few people really have got a grip on the basics of electricity. This simple diagram illustrates the four parts of a useful electric circuit. We have, first of all, the generator or the source of electricity. Could be a battery, could be a generator. Next, we've got the load. The load is what gives us the benefit. It's doing some type of work. Motors turning, heat is being released, light is being created, and between the load and the generator, there's normally a switch. And the switch can be open like this, or it can be closed like this. And when it's closed, that's when the electricity flows and the work gets done, the heat gets created or light gets created. And the other part of the circuit is the conductors. Okay, we have a conductor. The black conductor is normally in a household, is the hot conductor. It goes over to the load. Out the other end of the load comes a white wire and back to the generator. Now, the generator is like an electron pump. And what the generator does is it pumps electrons out of the ground and gives the electrons a charge of energy. And then it moves the electrons through the load and back around to the other side of the generator. So when an electron enters the generator from the ground, it is at a low energy level. And the generator gives the electron energy. And it comes out, now we have an energized electron on its way to the load. The electron, I like to think of it as little soldiers with backpacks, and they're carrying a certain amount of energy. Each soldier is carrying a certain amount of energy on their back, and they go over here and they unload the energy right here at the load. And then they continue on their way with their backpacks empty, and they come around and they're re-energized again, or they go back into the ground. We don't need to be too concerned about what happens here. But the ground, we know, is the infinite donator of electrons and the infinite electron sink. That's why circuits are connected to the ground, because you have a source of electrons and you have a place to dump the electrons that have already done their job, or let the electrons rest, maybe. They're little soldiers, so we're going to take them back to the ground and let them rest and then bring them back and make them carry some more energy. So now let's talk about how we measure the energy that these little electrons carry for us. Okay, let's start off and define the two terms, power and energy. Power is the instantaneous amount of energy that's drawn through a particular circuit by the load from the generator. We say it's drawn because it's not really being used, because it's just happening at an instant. We're just looking at the instantaneous power draw. We say the power is drawn, and we say that the energy is used. The energy is used because the power is drawn for a period of time. So power times time equals electrical energy. And so the way to understand it, I think, is to go back to the very basic units. We have the units that we use for electricity aren't the most basic ones. There's some units standing behind, the volt and the amp and the watt that will help you, I think, understand just how energy is imparted to a group of electrons and how they go down, they march down the conductor and unload this energy at the load and then come back to the source. So let's talk about what these units behind the scenes are. There's three important units. One is the joule, and a joule is a very small unit. 1,055 joules is equal to 1 BTU, 1 British thermal unit. British thermal unit is equal to about the energy in a kitchen match. And it takes 1,055 joules to equal 1 BTU. So it's a very small unit of measurement, but it's energy. And then time, we're measuring in seconds. That's easy to understand. But charge, this is the number of electrons. This is the number of little soldiers that we have to do our work. And we need them. And they're measured in coulombs. And a coulomb is a very large number of electrons. It is, in fact, about 6 times 10 to the 23rd. So a 6 with 23 zeros would give you around the number of electrons. Let's not even think about that. That's just too big, but it's just a number of electrons. A coulomb is a number of electrons. So I think everybody who has learned much about electricity has seen this formula, that the volts times the amps equals the watts. Okay, if we just have a household circuit, 120 volts, and we have 1 amp running through a load at 120 volts, that would be a draw of 120 watts. We could say that the load was drawing 120 watts of power because there was 1 amp of flow, of electrical flow, going through the load at 120 volts. So 120 volts times 1 amp would be 120 watts of power being drawn by the load. Let's look at the units behind that. A volt, what is a volt? Well, they say it's electrical pressure or potential difference or a lot of these terms, and they're not too descriptive of actually what a volt is all about. A volt is the amount of energy that each coulomb of charge is carrying. It's like how much energy is in the little soldier's backpack, okay? And the amps, this is easier to understand because this is, how many soldiers go by a certain checkpoint at, in a certain period of time, coulombs per second. How fast are the electrons passing us through the load? So we know that if we have our units in a fraction like this, and we have a coulomb on the top and a coulomb on the bottom, we can cross out the coulombs if we're going to multiply these together. Volts is equal joules per coulomb, amps is coulombs per second. What does that equal? It equals a joule per second, and that's exactly what a watt is. A watt is a joule per second. And the reason why I wanted to explain this to you is that people get very confused about this unit because they know it's an instantaneous draw of power, but they don't see the unit of time in this unit. But a watt is a joule per second. If you just remember that, it'll be easier for you. So if we have 1 watt, a joule per second, and let's say that this was connected for 10 seconds, that means you're going to have 10 joules of energy was used. Or if it was connected for 100 seconds, that would mean 100 joules of energy were used. Now, in the everyday measurement of electricity, we don't use this. Okay, this is just, if it helped you to understand what's going on, that's fine. If it didn't, don't worry. Because watts is the instantaneous power draw, and if you times it by hours, you get watt hours. and 1,000 watt hours equals a kilowatt hour. And what we're talking about when we talk about watt hours and kilowatt hours is energy. We have to connect the load for a period of time before we've used any energy. Power is not the same as energy. Power is the instantaneous draw. And energy is once the power has been connected for a period of time, then energy has actually been used.